Up to now, we've treated logic gates like AND and OR as building blocks, but in real digital hardware, there's an interesting twist. We often don't build circuits using a mix of AND, OR, and NOT. Instead, it's very common to actually implement circuits using inverters plus one universal gate type. Usually, it's either an all NAND plus inverter implementation or an all NOR plus inverter implementation. This keeps things a little more efficient while we're still letting us hold on to the way that humans build logic in terms of ANDs and ORs. So when we say all NAND or all NOR, we usually mean the logic is built using only NAND gates plus inverters or NOR gates plus inverters. From an efficiency point of view, we actually want to keep inverters because inverters only have a couple of transistors to implement those in CMOS. And it turns out also that NANDs and NORs, as we've discussed, only take 4 transistors compared to 6 for AND and OR for 2 input gates. So there's some reasons to do all NAND, and historically, back when we had discrete chips, it also simplified inventory control to have just a whole stockpile of NAND gates and inverters rather than to have to keep a mixture of logic parts. So at the same time, even though the underlying circuits might be all NAND and inverters or all NORs and inverters, we want to preserve the logic of Boolean expressions. Human beings think better in ANDs and ORs rather than NANDs and NORs. So the goal is to come up with a system where we can play it both ways. So that's where De Morgan's theorem comes into play. It turns out if you use inversions, which we indicate with bubbles, we can take a look at the Boolean expression or the Boolean theorem for De Morgan's. De Morgan says that if you have A ANDed with B here on the right-hand side of the equation, you can break the line and change the sign and give an equivalent Boolean expression that's A bar or B bar. So we've drawn this out. Here's the OR function that comes from this plus symbol. And these are the inversion bubbles that give you A bar and B bar. Equivalent circuits. This circuit is the same as this circuit. Built into it is a little bit of the suggestion of OR functionality. And of course, built into this one is the AND functionality. Then we have bubbles at the end that we're going to see how this works out, where we basically cancel inversions or cancel bubbles to make things work together. Okay, you can click through here and confirm to yourself that no matter what combination we take on A and B, these two circuits produce identical outputs because it's just De Morgan's theorem. You can actually turn this logic around the other direction as well, where if you have A or B inverted, so that would be the NOR gate, okay? Well, with De Morgan's, that's equivalent to A bar and B bar. So you put inversion bubbles on the inputs and you get an equivalent circuit. And so you can check this out, that both of these circuits are equivalent. This has the built-in sort of memory trick that we know this is coming from an AND shape with inversions on the input, which is equivalent to a NOR gate. This will make more sense when we start to put circuits together. The next thing I wanted to tell you is that technically you don't have to have inverters at all if you use all NAND or all NOR, because if you tie the two inputs together for a NAND gate, it acts like an inverter. And this makes sense from a Boolean algebra point of view. A ANDed with A bar is equal to A bar. Okay, same thing with NOR. NOR is a universal gate, meaning you can build all logic functions out of it, including inversion. Okay, so that's De Morgan's theorem applied to gates. We're going to put together a couple of 2-level gate circuits to show you how this all works out. And you can do AND or implementations using either NANDs or NOR gates.